Okay, so this is chapter 5 in our textbook, which is Chang Chemistry, and it deals completely with gases. And let's get started by taking a look at the periodic table and talking about which elements actually exist as gases at 25 degrees Celsius, which is pretty much room temperature, what we call ambient temperature, in one atmosphere. And one atmosphere is a unit of pressure. So this is pressure at sea level on the planet Earth. And you can see that if you look at the entire periodic table, it's only a minuscule part of the periodic table that that is elements that are gases at room temperature. So everything that's in this teal sort of color here, these are all gases, things like hydrogen, nitrogen, oxygen, fluorine, chlorine, and the noble gases. So not very much, right? In fact, most of the elements exist as solids, and there's only two elements that exist as liquids, and those are mercury and bromine. So the two green circles, those exist as liquids. The ones in the green boxes or the green boxed in area, those all exist as gases, and the rest is all solid. So not very many elements exist as gases, but you should be aware of all of these elements that do exist as gases at room temperature and one atmosphere. In fact, when we look at compounds that are gases, so molecular compounds that are gases, there aren't that many compounds that are gases, as a matter of fact. Most molecular compounds are liquids or solids. And again, here is the list of elements that are gases at room temperature in one atmosphere. And one thing that you'll notice about some of them is that if you look on the periodic table, you see hydrogen as an element, right? But there's no H that just exists by itself on the planet Earth. When hydrogen is found in its pure form on Earth, it's going to exist as H2, right? Which is a diatomic molecule. So we put two atoms together and we make a molecule. Another example is oxygen or fluorine, right? On the periodic table, these are just, elements found like this. But again, you won't find those, and you won't find nitrogen, and you won't find chlorine just as gases as they are seen on the periodic table. They always combine to form a diatomic element, O2, F2, N2, or Cl2. And you'll probably also notice that there's another form of oxygen that exists as a gas, and we call this an allotrope of oxygen, and this is ozone. So O3 is the ozone molecule, and you've probably heard of things like the ozone layer. Now, if we scooch down to the bottom here and we look at all the different molecular compounds that exist as gases, you can see it's not a very big list. Okay, compared to the number of molecules that are liquids or solids, this is a very, very tiny list, very small list. Okay, let's go over these very quickly, but you should be aware of most of these, like HF, hydrogen fluoride, is a gas, as is HBr, as is HCl, and HI. Now, you might be thinking, well, what about something like HCl? I thought that was hydrochloric acid. Well, hydrochloric acid is a solution of hydrogen chloride, which is a gas, okay? So hydrochloric acid is this, HClAQ. And I've probably gone over that with you in class before, but that's just a refresher. So if you were to have hydrofluoric acid, hydrobromic acid, or hydroiodic acid, the formula will always be followed by AQ. But all of these HF, HBr, HCl, and HI, when they're in their pure form, they are all gases at room temperature. What else? Carbon monoxide. You've probably heard of carbon monoxide. Most people have a carbon monoxide detector in their home. Carbon dioxide is one of the gases that's present in our atmosphere. It's less than 1%, but you're probably also aware that carbon dioxide is a product of combustion. Methane is a major component found in natural gas. Acetylene is a gas that has many uses. In fact, it's mostly used in synthesis. But if you go talk to people on the street, where most people will know acetylene from is welding. It's used as the gas that's used in welding. Ammonia is a gas, nitrogen dioxide, nitrous oxide, nitric oxide, sulfur dioxide, hydrogen sulfide, hydrogen cyanide, which you can see is actually has a boiling point of 26 degrees Celsius, but it's close enough that it qualifies as a gas at ordinary atmospheric conditions. And another one here is sulfur hexafluoride. You've probably all tried, at least at one point in your life, you've probably all tried inhaling some helium and then talking, and it makes you, talk in a really high-pitched voice. Well, if you Google, you can actually, or search on YouTube, you can see videos of people inhaling sulfur hexafluoride and talking, and it makes them sound like, I don't know, Darth Vader or somebody. And the reason why is because the molar mass of air, the air that we breathe, has an average of around 30 grams per mole, whereas helium is only 4 grams per mole. And so the sound waves travel much faster, and so they have a higher pitch. And then in sulfur hexafluoride, well, it's a gas, but it's a lot heavier than air. And so the sound waves travel slower, and then you get that kind of low pitch sound there, which is kind of funny. Anyhow, let's move on and talk about some physical characteristics of gases. And this goes all the way back to talking about phases of matter. We know that gases will assume the volume and the shape of their containers. If you think about a liquid will take on the shape of its container, but it won't take on the volume, okay? Whereas a gas will always fill up the volume out of whatever container that it's in. And based off of that, if a gas is going to fill up whatever container that it's in, it stands to reason that gases are going to be the most compressible of all the states of matter. In a gas, the particles are simply farther apart than they would be in a liquid or a solid, and so we can compress gases. What else? Gases mix evenly and completely when confined to the same container, and so gases mix to form homogeneous mixtures. What else? Gases have much lower densities than liquids and solids. Well, that should kind of be obvious, generally speaking, that gases will have much lower densities than liquids and solids. Anyhow, what's in here? I'm not sure. I didn't look at the figure in the book, but it looks to me like it's bromine. So you might have some bromine liquid down here in the bottom, and then some bromine gas up at the top. So most molecular gases that we looked at in the previous slide, most of them are colorless, but some of them like NO2 or chlorine or fluorine, they do, or bromine gas, they do have colors. Anyhow, what are some other interesting facts about gases? It says here from the 17th century respelling of the pronunciation of the Greek word chaos. So that's where the word gases come from. I'm not really a historical authority to maybe give you more information than that. And I've heard that my whole life. Sometimes I've probably heard gas referred to as or vapors. They're also sometimes referred to as miasmas, not as commonly. Air is a mixture of gases, and if you don't know what air is mostly made of, well, it's, air that we breathe is mostly nitrogen. It's about 78% nitrogen and about 21% oxygen, and then I'll put 1% other gases like carbon dioxide and methane and little bits of noble gases. Anyhow, what else? Homogeneous mixtures exert a pressure. That's going to be important, right? Tonight we're going to talk about the pressures that gas exert. And we're going to even talk about what's the meaning of pressure, right? What's the meaning of pressure? And there we go. And then properties and behavior can be explained by treatment as ideal gases. I don't know if we're going to have time to look at that tonight, but we're going to look at some assumptions that you can make about the behavior of gases and that we treat them as if they are ideal gases. And you notice how ideal gases is in quotations. Ideal gases is just like an ideal, mate. There's no such thing, okay? But an ideal gas is an approximation that we can use that can be very helpful in doing calculations that involve gases. Anyhow, what else? The kinetic molecular theory of ideal gases. Now, this is going to come into focus more later on when we talk about ideal gases, but this was postulated a long time ago, the kinetic molecular theory of gases. And I want to take a quick look at it right now because it'll give us a little bit of insight about the properties of gases before we really get into some nitty-gritty on some of the gas laws, like Boyle's law, which is coming up in the next few slides. So the first one says that a gas is composed of tiny, discrete particles. Now, what does it mean by tiny? Well, you know what that means. It means small. Now, discrete particles means that the particles are separate from each other. Okay, if you think about a liquid, all the particles, whether they're molecules or atoms in a liquid, they're all next to each other. They're all in contact with each other, sliding past one another in the liquid phase. If you think about a solid, the same thing. In a solid, the position of the particles is fixed, but they're all touching each other, right? Whereas a gas, the particles are discrete, okay? The particles are in rapid random motion in a continuous straight line motion. Now, this is kind of an assumption that you have to make, but you can think about, you know, a particle of a gas moving in a straight line like this, okay? Um, anyhow, moving in a straight line like that, that's not really that great of a demo, is it? Anyhow, we'll talk about that more later. Um, the particles are far apart in comparison to their size. So here's one for you. Most of the volume of a gas is empty space. Now that might not be intuitive to you. You think, well, you know, how can I have just empty space? Well, that is true. You know, most of the volume of a gas is empty space because the particles are so small and they're so far apart. Lastly, ideal gases consist of particles that have mass but not volume. The particles are considered to be dimensionless points. Now, if you haven't read the textbook yet, and I hope you all have, you might be thinking like, whoa, 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 Mr. Dion, hold the phone here, buddy. How can you have a particle that has a mass, but how can a particle not have any volume? That's impossible, Mr. Dion. How can the gas have no volume if it's matter? I thought the matter took up space. Well, you would be true, or you would be correct in that assumption. But remember, we're talking about the theory of ideal gases, and I told you that ideal gases don't really exist, but it's a good approximation that we can use to do calculations that involve gases. Okay, so it's an assumption that we make that the particles do have mass, but they don't take up any space. So we think about them as little points that don't take up any space. Kind of maybe a little bit difficult to wrap your head around at 5:15 on a Tuesday, but anyhow, hopefully, as I said, it will come in even more into focus as we look at ideal gases in detail. And just to put this bug in your ear, for people who are really, really curious about ideal gases, you might be wondering, well, if you said, Mr. Dion, you said the ideal gas is, you know, there's no such thing as a perfectly ideal gas. Okay, sure. You might be wondering, you know, do we ever think about gases that aren't ideal? And the answer is yes. And that's at the very, very end of this chapter. We'll take a quick look at deviations from the ideal gas law. All right. Anyhow, with that in mind, let's get started at the real stuff here. You know, learning some new formulas and practicing some calculations that you could find on your next exam. And let's define pressure. And pressure is the force per unit area. If you think about pressure on a car tire, for example, it might say, you know, 90, oops, not like that. It might say something like 90 psi. You've probably heard of that before. And what's 90 psi? The psi is equal to the number of pounds per inch squared. That means that in 1 inch squared, this is not to scale, by the way, there's a certain amount of pressure, you know, of the gas on that square 1 inch. So pressure, again, is defined as force per unit area. And force is defined as mass times acceleration. Now, the units of pressure that you're going to have to know for this class, I'll be completely frank with you, are pretty much everything on here except for 1 Newton per meter squared. So if you remember earlier on when we looked at that table that said, okay, well, which elements and which molecules are gases at 25 degrees Celsius in 1 atmosphere? 1 atmosphere is the pressure on the planet Earth at sea level. So 1 atmosphere. So you can imagine that in Colorado Springs, we're not at 1 atmosphere, right? We're going to be below that because we're at a higher altitude, and so we have a lower air pressure. But that is equal to 760 millimeters of mercury, which is equal to 760 torrs. Now you may be wondering, what is this millimeters of mercury? What's the significance of that? Well, let me explain it to you. Okay, a long time ago, a scientist by the name of Evangelista Torricelli did a famous experiment. Evangelista Torricelli, you can probably guess Torricelli sounds like an Italian surname, and he was an Italian scientist. And Italy is surrounded by the ocean, or at least a lot of it is surrounded by the ocean. And so he went down to the seaside in Italy, and he did this nifty experiment that is shown right here. Okay, and what he did is he had a dish of mercury metal. You know, you might be thinking, well, mercury's toxic, you know. Yeah, but he still used it for the experiment because it's got such a high density. Anyhow, and what he did was he filled up a tube all the way to the top with mercury, and then he quickly inverted that tube. So first he had the tube right side up like this, and it was filled with mercury all the way to the top, okay? And then what he did is he went, "Acha!" and he tipped it over, and he put it upside down into the pool of mercury. And what he found is that the mercury dropped down a little bit in that tube, and if he measured the distance of from the top of the mercury to the top of the liquid in the dish, he found that it was 76 centimeters. Now, if we know 76 centimeters, and we know that in 1 centimeter there is 10 millimeters, right? We do a little dimensional analysis here, and we see that that's equal to 760 millimeters of mercury. And so that is a standard that we use. We say that 1 atmosphere, or the pressure at sea level, is equal to 760 millimeters of mercury. This is one that annoys students sometimes. The millimeters of mercury shown here and torr are the same thing. They're the exact same thing. No conversion factor required. They mean the same thing, but torr is obviously named after Torricelli. Okay. Also, sometimes we're going to be looking at pressure in terms of pascals, because again, 1 pascal is equal to 1 Newton per meter squared. I should point out that pascal is not small p. This should be an uppercase P. Anyhow, it should be 1 pascal, should be 1 big PA. Anyhow, when you fix it, is 1 Newton per meter squared. And then you can see that 1 atmosphere is equal to 101,325 pascals. And another way that you can express that is to say 1 atmosphere is equal to, and I like this one a lot more, 101.3 kilopascals, right? Because you can imagine that there's 1,000 pascals in 1 kilopascal, right? Kilo, the prefix, we think 1,000. Okay, so with all that information in mind, let's try a question. It's not meant to be a mind boggler. It's just meant to see if you can convert the units of pressure. The pressure outside a jet flying at high altitude falls considerably below standard atmospheric pressure. Therefore, the air inside the cabin must be pressurized to protect the passengers. In fact, where most commercial airline, jets fly, if you were to be exposed to that atmosphere, if you could just move sit the plane immovable in the sky, because otherwise you'd fly off, right? But if you could be exposed to that atmosphere, you wouldn't be able to breathe because the air is so thin. Okay. Anyhow, so let's figure out what is the pressure in atmospheres if within the cabin, the barometer reading is 688 millimeters of mercury. And I'm not going to ask you guys about this one. I'm just going to help you out with the conversion factor here. Is because we know from the previous slide that in 760 millimeters of mercury, we have 1 atmosphere. Now remember, when we're dealing with a conversion factor like this, we can assume that the two numbers 760 and 1 have an infinite number of significant figures. All right, let's get started with the math. And let's start like this. We have 688 millimeters of mercury. We want to multiply that by a conversion factor, and we want to end up with atmospheres, ATM, like that. What's the conversion factor? Well, we know that we have 760 millimeters of mercury in 1 atmosphere, like that. Look at this. Millimeters of mercury cancel. 688, where's my calculator? 688 divided by 760. I get 0.905 atmospheres. Nothing more than that. Give me a thumbs up if you think you can tackle that one. Thank you, Mr. Dion. Just make the whole next exam that question. I am going to. Good, great. Thanks, Tyler. All right, Julius, Chris, Trevor, gang. Excellent. Yeah, just a little bit of conversions with the units of pressure. Let's try another one here. It says the atmospheric pressure in San Fran on a certain day was 732 millimeters of mercury. What was the pressure in kilopascals? Well, you might remember that the last conversion factor I think I wrote down a couple of slides ago was that 1 atmosphere is equal to 101.3 kilopascals. And thus we can use that conversion factor because we started with our 732 millimeters of mercury. We have our conversion factor, which was 760 millimeters of mercury is equal to 1 atmosphere. And then we know that 1 atmosphere is equal to 101.3 kilopascals, like that. Let's double check. Millimeters of mercury cancel out, atmospheres cancel, and we end up with 97.6 kilopascals, like that. Now, I've done this problem before a couple semesters ago with students, and one of them just said, well, why couldn't I solve it like this, Mr. Dion? Why couldn't I just say 732 millimeters of mercury and then go back here? And so what the student said is, if all of these are equal, right? If 1 atmosphere is equal to 101.3 kilopascals, and 1 atmosphere is equal to 760 millimeters of mercury, why do you need two conversion factors? Why couldn't you just do it like this? So why couldn't you just say, say that in 760 millimeters of mercury, you have 101.3 kilopascals, like that. Why couldn't you do it that way? And the answer is you can do it that way. There's nothing wrong with that at all. You're still going to get 97.6 kilopascals. You'd end up with the exact same answer. Okay, so either way is perfectly acceptable. Any questions about that one? Any burning questions? All right, well, then let's take a look at devices that we could use, or a device that we could use to measure gas pressures. I've used this, these are called manometers. Sometimes you'll hear them pronounced manometers. I didn't hear that until I looked on YouTube and somebody called it a manometer. I've only ever heard it called a manometer. Anyhow, so a manometer, a manometer can be used to measure gas pressures, and you see that we have two pictures here, or two figures, and two different types of manometers, A and B. And A is a closed tube manometer, and B is an open tube manometer. And the closed tube is exactly what you think. You can see that this tube is closed here, and so there's a vacuum in here. So if we have, what we do is, with the closed tube, we start it with equal heights of mercury, okay, which isn't shown here, but you start it with an equal height, and then you open up the stopcock, or you put the gas in here, depending on the type of manometer. Sometimes there's a stopcock here. Anyhow, I digress. But the way that you measure the pressure of this gas right here is that it's going to be directly proportional to the height of mercury, right? How hard can the gas push this whoop up the tube, like that? And so when we have a closed tube manometer like that, if the pressure of the gas, and I should write this down, that in this case, where is it here? If the pressure of the gas is less than the pressure of the atmosphere, so we usually use this to measure gases that have a low pressure. I didn't mean to do that. Okay. Where was I? Then we can see that the pressure of the gas is going to be directly proportional or equal to the height of the mercury. So we measure the height of the mercury in millimeters, and of course we can relate that to millimeters of mercury, or torr, or atmospheres, or pascals, or kilopascals, what have you. Now, in an open tube manometer, we have the atmosphere pushing against this, right? Because this is open to the air. So you have the pressure of the atmosphere pushing down right here. And so, yes, the gas, you can see the gas is clearly pushing the height of the mercury up like this. So we do have to take this height into account, but it's also pushing against the atmospheric pressure. And so when you want to measure the pressure of the gas in the open tube manometer, okay, you are going to have to add the height of the column of mercury and atmospheric pressure to it, right? Because it's got to even overcome the atmospheric pressure to even get the height of the column to raise at all. Now, I should also point out that this is a specific case where this would apply when the pressure of the gas is greater than atmospheric pressure. Now, you might be wondering, what about this whole gas greater than atmospheric pressure, gas lower than atmospheric pressure thing? Well, I try to clear that up on this next slide right here. So let's take a look. And it says here to measure the pressure of a gas, okay, if we have an open tube manometer, okay, we've got two different scenarios. The first scenario is you can see that the height of the mercury here is lower than the height of the mercury here. That tells us that the pressure of the gas is less than atmospheric pressure, okay? Less than atmospheric pressure. Because if it was higher, if the pressure of the gas was greater than atmospheric pressure, it would look something like what's shown in this manometer here, pressure atmosphere, right? Because not only is it higher, but it's pushing against the atmosphere. Sorry, I should just say this side is higher, and it's also pushing against the atmospheric pressure. And so to summarize, if you want to measure the gas pressure using an open tube manometer, when the gas pressure is less than atmospheric pressure, you take atmospheric pressure and you subtract that height of the column of mercury, okay? If you want to measure the gas pressure when it's greater than atmospheric pressure, you take the height of the column of mercury and you add atmospheric pressure to it. Or I should have said maybe you measure atmospheric pressure and then you add the height of the column of mercury to it. Okay, so two different scenarios. All right. Well, with that in mind, let's keep both of those scenarios in the back of our hat, okay, or up our sleeve. And let's look at a problem here that deals with a manometer. It says, what is the pressure of the sample of gas trapped in the open tube mercury manometer shown below if the atmospheric pressure, so P atmosphere is equal to 736 millimeters of mercury, and the height of this column is 9.2, so H is equal to 9.2 centimeters. And we can convert that into millimeters pretty quickly because we know that in 1 centimeter there's 10 millimeters, and so that would equal 92 millimeters of mercury. Okay, well, let's see here. What scenario are we dealing with here? Is the pressure of the gas less than atmospheric pressure, or is the pressure of the gas greater than atmospheric pressure? I'm going to throw that out to my students. I put both of the formulas on here just to try to make the question a little bit easier for us to think about it. I kind of put it in a goofy spot, but hey, could anybody tell me which scenario we're in here? Is the pressure of the gas less than or greater than atmospheric pressure if the height of the column of mercury is lower over here, where the atmospheric pressure is pushing down? Yes, thanks, Julius. Yes. So this is the scenario that we're in, right? The pressure of the gas is less than the pressure of the atmosphere, okay? And so we're going to have to use this formula here. So we're going to take our atmospheric pressure and we're going to have to subtract the height of the column of the mercury. And so the pressure of our gas is going to be equal to the pressure of the atmosphere, subtract the height of the column. Instead of mercury, I'm just going to write Hg like that, which is the atomic symbol. And so we have 736 millimeters of Hg, subtract 92 millimeters of Hg like that. And that's a pretty simple calculation to do in your calculator, and you end up with the pressure of the gas being equal to 644 millimeters of mercury. This one right here, B. Okie doke. So a manometer problem. Usually I put maybe one problem that deals with manometers on the practice exam and one problem on the actual exam. Let's take a look at one more here. Again, I put the formulas here to kind of help guide us through the solution. Sometimes it's easier to do that when you're just learning something. Up above, what does it say? Hey, can anybody tell me what's going on here with the pressure of the gas? In this case, is it greater than atmospheric pressure or lower than atmospheric pressure? Remember, the atmosphere is pushing down right here because this is open-ended. Would the pressure of the gas, so my question is, would the pressure of the gas be more or less than atmospheric pressure in this specific example? We didn't even read the problem yet. I'm just looking at the manometer. Yeah, absolutely, it's more, right? Yeah, so this is an example where, maybe I should just delete this, where the pressure of the gas, P gas, is greater than the pressure of the atmosphere, right? You can see you got the pressure of the atmosphere right pushing down on the mercury right here, but the mercury is like, heck no, I can push back against you even harder. And so that tells you that the pressure of the gas is higher. And so we're going to need this formula right here. Now, I'm getting a little bit ahead of ourselves here, but let's take a look at the question. It says on a certain day, the barometer in a lab indicates the atmospheric pressure is 764.7 torr. A meter stick is used to measure the height of the mercury columns above the manometer. The level of the mercury in the open-ended arm has a height of, so that means, it says here, the level of the mercury in the open-ended arm has a height of 134.6 millimeters, and that in the arm in contact with the gas is 103.8 millimeters. What is the pressure of the gas? So you can kind of ignore this 25 centimeters that I have here. That's an artifact from something else, I guess, that I took. What I'm trying to say here is this. In this problem, if you measure from the bottom of the mercury and you measure to the top of this point here, this distance is 136.4 millimeters. And you can put millimeters of mercury, but since it's mercury, or you can just put millimeters. And this height right here is, what is it? 103.8 millimeters. So if you say delta H is equal to 136.4, subtract 103.8 millimeters. Have I done that? I'm looking at my notes here. Yes, you end up with the delta H being equal to 32.6 millimeters, like that. So that's this delta H. Let me write it in here for us. Delta H is equal to 32.6 millimeters of mercury. Okay, now that we got that settled, now we can use our formula. Another thing I want to ask you is, if I have an atmospheric pressure of 764.7 torque, can somebody tell me how many millimeters of mercury would that be? And it's not a trick question. How would I get the, yeah, thanks, Julie. Yes, exactly, okay? Nothing more than that. It's going to be equal to 764.7 millimeters of Hg, like that. Okay, now we've got everything we need, because we know this height is in millimeters of mercury, and we have our atmospheric pressure. We can use this formula right here, and we'll say that the pressure of the gas, okay, is equal to atmospheric pressure, which is 764.7 millimeters of mercury. And then we're going to subtract the height of the column of mercury. Did I circle the wrong one? I did. Should be on losing it. Yeah. Fix that. That's not right. I'm supposed to be adding this and subtracting. There we go. So again, the gas pressure is greater than atmospheric pressure. So we add that height, and we have 32.6 millimeters of Hg. When you put that in your calculator, you get a total of 797.3. So 797.3 mmHg. So that's the answer, but all the answers that it gave us are in atmospheres. So we have one more step, and that's just to convert that pressure, which is 797.3 millimeters of mercury, and we're going to convert that into atmospheres, because we know that in one atmosphere we have 760 millimeters of mercury. So there's our conversion factor. Millimeters of mercury cancel, and we end up with 1.05 atmospheres, like that. And that's it. That's the answer to the problem. Look, I understand that everybody who's hearing the sound of my voice can add and subtract. There's nobody who can't add and subtract. And all these past two problems is addition and subtraction. What's the tricky part? Interpreting the problem. Nothing more than that. It's being able to look at the manometer and say, well, the pressure of the gas is greater than that of atmospheric pressure. So I'm going to have to add the height of the column of mercury to the atmospheric pressure, or the pressure of the gas is less than atmospheric pressure. I take atmospheric pressure and I subtract the height of the column of mercury. That's it. Okay. Here's something interesting for you. And this is an experiment that was also done a long time ago, and it was used to study the relationship between pressure and volume. Now, for pressure, we use the variable P, and for volume, we use the variable V, like that. And if we take a look at this glass tube, you're like, whoever was interested in gases was obsessed with glass tubes. Well, maybe. Anyhow, if we have an open-ended glass tube, like shown right here, and we have a certain amount of mercury in there, Okay, so I'm going to walk you through what's happening. We have that certain amount of mercury in there, and you can see that the volume of gas in this closed end of the tube is 100 milliliters. Now, what happens here is if we double the amount of pressure, okay, so we're starting with, or double the amount of mercury, I should say, so that we double the pressure, okay? What happens is that the volume gets cut in half. You see how we go from 100 to 50? Okay, well, look what happens, and it's probably easier to see here, that as we take our pressure and we go from a pressure that's equal to 760 millimeters of mercury, and we double that pressure, right? 760 times 2, let me double check myself. Yeah, it's 1520. Okay, if we double that pressure, what happens to the volume? It goes down. Okay, so, but what's the overall relationship that we're seeing here? Okay, what we're seeing is that as the pressure increases, what's happening to the volume? The volume is going down. And so that tells us that we have an inverse relationship. Okay? Inverse relationship between pressure and volume. And we can write that as pressure is proportional to the inverse of the volume, like that. Now, if we, I'll just leave it at that for now, because I want to move on to the next slide, which is Boyle's law. And that is, if you plot, you see there's two graphs here, one of them is linear, one of them is not linear. If you simply plot pressure versus volume, okay, what you see is that you end up with this curve. And what's the take-home message from this curve? Two things, okay? So right now we're just looking at A, okay? As we decrease the pressure, right, as the pressure drops, goes this way, what happens to the volume? The volume increases. So again, we can see that that's an inverse relationship. But this is what I stopped myself from saying on the previous slide, is this right here, is that we notice that whenever we take a data point anywhere on this line, okay, anywhere, and they've chosen two specific spots. They've chosen this spot right here. Where's my green highlighter? This spot right here, and they've chosen this spot right here. And they said, if you multiply the pressure times the volume at any point along that curve, you end up with a constant. Don't believe me? Let's try it. If you take 2, okay, so at this first point right here, if you take 2 and you multiply it by 0.6, so let's take 0.6 times 2, you end up with 1.2. Okay, so P times V at that first spot is equal to 1.2. And we'll just forget about the units for now. We'll just leave it out. Okay, if we do the same thing at this point right here, what do we have? We have 4 and 0.3. If you take 4 and you multiply it by 0.3, what do you get? 1.2. So again, we see that P times V is equal to 1.2. We can rewrite that expression to say pressure times volume is equal to a constant K, like that. Okay, and since that K doesn't change, okay, that K doesn't change, you can see that it didn't change here. Based off of that, we can rewrite that expression since K is always the same. What if we have two different data points? We can compare the two. We can say the pressure and the volume at the first data point, their product is going to be equal to the product of the pressure and the volume at a second data point. P1 times V1 is equal to P2 times V2. That's shown right here. Okay. Now, if you plot pressure versus 1 over volume, you get a linear graph, right? Which is of the form y is equal to mx plus b. Okay, so we have a linear slope like that. Okay, and this is called Boyle's law, which shows the relationship between pressure and volume. Now, there's something I've left out along the way. Two things is that when we want to use this expression, because students love to use these kind of formulas, because as long as you know 3 of the variables, you can plug them in and solve for the other variable, right? Let's say, for example, we wanted to solve for V1. We could rewrite this formula as V1 is equal to P2 times V2 over P1. You should be able to do that, right? Simple algebra. But before we do that, again, and I'm taking a little bit of time to get to it, is that you got to understand that if we want to apply this formula, we've got to be at constant temperature and a constant amount of gas. Those two variables have to be constant. The variable that we use for temperature is T, and the variable that we use for the amount of gas is N. And if some of you have studied chemistry before, you've probably heard of, the ideal gas law, PV is equal to nRT, and we're getting there. Okay, but again, in order for us to apply Boyle's law, P1 times V1 is equal to P2 times V2, the temperature and the number of moles, or the amount of gas, has to remain constant. Now, where would we see Boyle's law in everyday life? Well, you're using it right now, because hopefully you're breathing while you're listening to me talk about this. And if you think about inspiration and expiration with the human lungs, or any lungs, I suppose, they are based off of Boyle's law. Think about it. When you breathe in, what are you doing? You're increasing the volume of your lungs. If I breathe in, my chest goes out because I'm taking air into my lungs. But why is the air going in? It's because the volume is getting bigger and then the pressure is decreasing, right? And you're like, well, I'm just sucking the air into my lungs. Yeah, but what's happening actually is that the pressure in your lungs is dropping below the atmospheric pressure. And so air is going to go into your lungs like that. When you exhale, which is the process of expiration, the opposite happens, right? When you breathe out, your chest relaxes, it goes down, the volume of your chest drops. Okay, so what does that mean? The pressure in your lungs is getting higher. As the volume drops, pressure goes up. Okay, and so that's going to cause air to leave your lungs like that. Okay, so Boyle's law in everyday life, and I'm sure that you can all come up with another example of Boyle's law, but in the interest of time, let's keep moving on. Here is the relationship between volume of gas and temperature, right, at constant pressure. All right, so in Boyle's law, again, we were talking about pressure and volume. And here we go. Can you all still see my slide that says variation in gas volume with temperature? Okay, good, thanks. Perfect. All right, so just to clear the air, we're moving on. Okay, we've moved on from Boyle's law. We've covered that. We're going to come back to it, of course, but right now we're on to the relationship between volume, okay, volume and temperature at constant pressure, and we could also put here and constant, and so constant number of particles. This is a really simple experiment. Okay, if you take a little capillary tube, so this is not to scale. It kind of looks like a test tube the way that it's drawn. But a capillary tube is a tube. If you're in group A, you saw those capillary tubes that we used to do the boiling point and the melting point. Okay, that's a capillary tube. So it's very thin. If you put a little bit of gas in the bottom of a capillary tube and then you put some mercury on top of it, if you have it at low temperature, okay, the gas is going to take up some kind of volume. And then you can see that as the temperature increases, what happens here is that the volume is going to go up, right? This is V1, this is V2. So as the temperature increases, the volume increases like that. And so we can see that volume is directly proportional to temperature. All right, okay. Now, if we do a similar kind of plot, we take the same kind of concept that we did with Boyle's law, we can do a plot of volume versus temperature, and that's what's shown here on this graph. The reason there's 4 different lines is because it's done at 4 different pressures. But if we just focus on one of those lines, let's focus on the P1 line, for example, a plot of volume versus temperature, you can see that there's a linear slope. Okay, there's a linear slope here. What does that tell you? It tells you that the volume and the temperature are directly proportional. Okay, we could also rewrite that as is shown here, or even better form, which is that volume over temperature is equal to a constant K. Well, if volume over temperature is equal to a constant K, then I could say that the volume at one data point over the temperature at one data point is going to be equal to the volume at another data point over the temperature at another data point. And that is what we call Charles' law. Okay, that's Charles' law. Now, this is at constant pressure, right? So constant pressure in constant number of moles. There is another relationship, which is related to pressure and temperature. And that is what we call Gay-Lussac's law. Okay, and I'm not going to spend a lot of time on Gay-Lussac's law right now, but Gay-Lussac's law is that pressure is directly proportional to temperature. Okay, and therefore we can write the formula P1 over T1 is equal to P2 over T2, like that. So here are the new laws that you have to know. Boyle's law, just summarizing here to kind of keep us all, straightened out. Boyle's law was this: P1 V1 is equal to P2 times V2. Charles' law, which is V1 over T1 is equal to V2 over T2. In Gay-Lussac's law, so this is two different people here. Gay-Lussac's law is P1 over T1 is equal to P2 over T2. Like that. Another thing, before we start to apply any of these laws, Boyle's law, Charles' law, or Gay-Lussac's law, okay, you've got to know that temperature is always going to be reported in Kelvin. Okay, and that way we avoid negative temperatures. Okay. Here's just an explanation of those two laws that we just looked at. Let's start with Charles' law. It says at constant pressure and number of moles, the volume and temperature, are directly proportional. If temperature goes up, volume goes up. If temperature goes down, volume goes down. Fine. At constant volume and number of moles, temperature and pressure are directly proportional. If temperature goes up, pressure of the gas is going to rise, which makes sense because if the volume is increasing, it's going to put more pressure on the walls of the container. And then if the temperature goes down, the pressure is going to go down. And that is Gay-Lussac's law. So that's just kind of a summary. And before we can get away and start looking at some problems in a few seconds here, I got one more law for you. I promise this is the last one until we get to the ideal gas law, and this is Avogadro's law. Yeah, named after the same old Avogadro from Avogadro's number. And what we see with Avogadro's law is that volume is proportional to the number of particles of gas that you have. Okay, let's take a look here. Here's a balanced equation. If we take 3 hydrogens and we combine it with 1 nitrogen, we end up with 2 ammonia. Okay, so what does the author really want you to know about this slide, and what does your teacher really want you to know? We have 3 of this gas and 1 of this gas. Okay, so that takes up a certain amount of space, right? 3 volumes for this one, 1 volume for this one. Now, if you're thinking, whoa, Mr. Dion, nitrogen is smaller than hydrogen. Remember, we're assuming that these gases have the same volume. Okay, we're assuming that they're ideal gases. Okay, they take up the same amount of space. So if I have 1 molecule, it's going to take up the same amount of space, whether it's hydrogen or nitrogen. Okay, and I'm forming 2 molecules of ammonia. This. Okay, so I'm starting with 3 volumes, of hydrogen, 1 volume of nitrogen, and I'm ending up with only 2 volumes. Okay, now the way that, and if you're like, well, what the heck is going on here? Look, all you really need to know is what's summarized right here, is Avogadro's law, is that volume is proportional to the number of moles. Okay, and we could rewrite that formula as volume over the number of moles is equal to some kind of constant K, or we could say that volume 1 over number of moles 1 is equal to volume 2 over N2. And so that's Avogadro's law. If you're still trying to connect all these laws, let's take a look at this one here. It says Avogadro's law. You can see that in the first example, we've got how many particles here? Let me count. We've got 1, 2, 3, 4, 5 particles. And there's a certain pressure and volume associated with that. We're keeping the pressure constant. So what's going to happen is if we add more matter, right, we go to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We double the amount of particles, what's going to happen is that the volume is going to double. And you see how the volume is higher in the second one. Then we double that again, and you can see how the volume increases. Okay, I always think of Avogadro's number, or Avogadro's law is kind of like this. Well, the molecules take up room, and so the more molecules I add, the volume is going to go up like that. Okay, let's move on from there. I think, yeah, summary of gas laws. So Boyle's law, Charles' law, all shown here. Yeah. Okay. So based off of that, we can, based off of those 4 laws, okay? Now, this is a lot of information. Mr. Dion's not crazy, okay? He knows that he's covered a lot of information. Let's summarize again. We got Boyle, okay, which is P1 times V1 is equal to P2 times V2. We've got Charles, which is V1 over T1 is equal to P2 over T2, like that. We've got Gay-Lussac, I'll put GL law like this, which is P1 over T1 is equal to P2 over V2. And then we've got Avogadro's law, Avogadro, which is the volume over number of particles is equal to volume 2 over number of particles 2, like that. So again, here are the first 4 gas laws that we've covered this evening. Okay. Now you can combine these gas laws all together. Okay. And if you're wondering, well, how the heck would I do that? Well, if we have all of these gas laws combined, okay, we can make a combined gas law. I'm not going to go into the derivation of it, but the combined gas law is this. Okay, so combined gas law kind of combines Boyle's law, Charles' law together, okay, and we can rewrite P1 V1 over T1 is equal to P2 times V2 over T2, like that. So this is our combined gas law. All right, with that in mind, let's take a look at a problem. It says the pressure on a sample of a gas is doubled and its temperature is tripled. By what factor does the volume change? Now you can see here that I have kind of mixed all of the formulas together like this, but what's staying constant in this problem is that the number of moles isn't changing, right? We're taking a sample of gas and we're not changing the number of moles. So N is constant in this problem. Okay, so we can cancel out the N, and that gives us our combined gas law. P1 times V1 over T1 is equal to P2 times V2 over T2, like that. Now it says that we're taking the pressure and we're doubling it, and we're taking the temperature and we're tripling it. How does the volume change? Well, this is just a matter of plugging some numbers in. If we assume that P1 is equal to 1, if we assume that V1 is equal to 1, and T1 is equal to 1, like that, what do we know about P2? It says here the pressure of the gas is doubled. That means it's going to be twice as much. What's 2 times 1 is equal to 2? We're trying to figure out how much the volume changes, so we're trying to solve for V2, and it tells us that the T2, the temperature is tripled. So what's 3 times 1? It's 3. And so now we have all of the knowns that we need to solve for V2. And you should be able to rearrange this formula to solve for V2. All right, you should be able to write out that with relative ease, that V2 is equal to P1 times V1 times T2 divided by T1 times P2, like that. Okay, now we can just plug our numbers in. We have 1 times 1. Our T2 was 3. Our T1 was a 1. And our P2 is 2. Now you can pretty clearly see what the heck is going on here. These are all going to cancel out, and we get 3 halves. So we get 1.5 or 3 over 2. So that's the factor that the volume is going to change. It's going to increase by 1.5 times. 1.5 or 3 over 2. Either way, it's the same thing. All right. with that in mind, let's give this one a try. You know what? Let me give you guys a second to take a look at this one. It's using the same thing, the ideal gas law, or sorry, the combined gas law rather. It says here that if the pressure of a gas sample is quadrupled and the absolute temperature is doubled, by what factor does the volume of the sample change? Remember, this is a gas sample. N is constant. N is constant. And so we can cancel that out to get the combined gas law, which is P1 times V1 over T1 is equal to P2 times V2 over T2. I'm going to give you a second and see if you can solve this one. Is it already 6 o'clock? Is anybody able to solve this one? By what factor does the volume of the sample change? Somebody says a half. Bruce, I think you're in the right vein, right? Okay, because our P1, so if we say our P1 is 1, our V1 is 1, and our T1 is 1, what's happening to our P2? The pressure of the gas is quadrupled, goes up by 4. The volume is what we're looking for, and the temperature is doubled. So we solve for V2. We did this a few minutes ago, but V2 is equal to P1 times V1 times T2 divided by T1 times P2. And then we get 1 times our T2, which is 2, divided by 1, and our P2 is 4. So these cancel out. We get 2 over 4, which is equal to a half. Exactly. So what happens to the volume? We can say here, volume is going to decrease by 1/2, like that.